It's one of the largest supervolcanoes in the country, and recent work out of the University of New Mexico led to a breakthrough discovery that could help geoscientists better predict an eruption and save lives.
Yellowstone National Park, one of the most iconic and geologically volatile regions in the United States, has recently become the focus of urgent attention following a startling discovery. Officials have issued a red alert after deep spreading cracks were found forming in multiple locations across the park's surface. The presence of these fissures has caused significant alarm among geologists, park officials, and emergency preparedness teams, raising fresh questions about the stability of the region and the underlying volcanic forces that have long simmered beneath its surface. Before we start, smash the like and subscribe buttons for more updates. The discovery was made during routine monitoring of thermal and seismic activity within the park. Aerial surveys revealed elongated fractures splitting across areas of crust near Norris Geyser Basin and close to the Sour Creek Dome, zones long associated with subterranean heat and pressure. On-site teams confirmed the presence of these cracks, some extending for several hundred feet, cutting through trails, meadows, and rock faces. What made this discovery particularly concerning was not just their length or spread, but the measurable rate at which some of them appeared to be widening. In some locations, the ground had shifted perceptibly over a matter of days, suggesting an active, dynamic process at work beneath the crust. Yellowstone has always existed under the looming presence of its supervolcano, an enormous magma chamber spanning dozens of miles beneath the Earth. This magma reservoir has erupted catastrophically in the past, most notably around 640,000 years ago, reshaping the entire region in one of the largest volcanic events on Earth. Although such eruptions are rare on human timescales, the signs of geologic unrest, including ground deformation, increased seismicity, and temperature anomalies, are constantly monitored by the United States Geological Survey (USGS) and other agencies. The recent emergence of surface cracks adds a new dimension of urgency to these efforts. Crack formations in volcanic areas are often symptomatic of deeper processes, particularly the pressurization of underground magma or hydrothermal fluids. As molten rock or superheated water seeks paths of lower resistance, it can exert enough force to fracture solid rock, allowing gases and heat to escape. These fractures, if they continue to propagate, can act as conduits, accelerating the destabilization of the surface and potentially leading to geyser eruptions, hydrothermal explosions, or, in worst-case scenarios, volcanic activity. The appearance of such extensive cracks in Yellowstone suggests a meaningful and potentially hazardous shift in the subterranean equilibrium. Adding to the concern is the location of these fractures in geologically sensitive zones. The Norris Geyser Basin is one of the hottest and most dynamic thermal areas in Yellowstone, known for irregular and unpredictable activity. It has been closely monitored for years due to its extreme heat output and its proximity to known uplift zones. Geologists had already noted minor swelling of the ground in this area over the past year, evidence that magma or heated water was moving below. Now, the visible cracking at the surface may be a sign that the upward pressure has reached a threshold capable of reshaping the landscape. Furthermore, the cracks have not remained isolated to thermal zones. Reports from hikers and rangers indicate fissures forming along higher elevation ridges and even along portions of road infrastructure. While some of these may be the result of natural erosion or frost heaving, the timing and pattern of the cracking strongly correlate with subsurface pressure changes. Roads have been closed and trails rerouted as a precaution, while scientists rush to install additional ground sensors to capture any shifts in real time. The Red Alert Declaration is the most serious issued in recent years, representing a heightened state of geological monitoring and public caution. It reflects not only the physical signs observed, cracks, ground uplift, and thermal changes, but also the uncertainty of what may follow. The cracks themselves may not lead to an eruption, but they are physical evidence that something is happening beneath Yellowstone's surface, something that current models may not yet fully capture. What makes Yellowstone particularly daunting from a geological standpoint is the scale of its underground system. Unlike traditional volcanoes that are built around a single vent or peak, Yellowstone is a caldera, essentially a collapsed volcanic crater that spans roughly 30 by 45 miles. Underneath lies a vast chamber of semi-molten rock, layered in complexity and connected through a network of faults, heat pockets, and fluid reservoirs. This means that any surface activity, like the sudden appearance of cracks, must be interpreted as part of a much larger and interconnected system. These new fissures are not merely aesthetic scars on the land. They could act as pressure release points or, conversely, pathways that allow even more heat and gas to migrate toward the surface. If the latter proves true, geysers could erupt more violently, steam vents could widen into boiling mud pots, and entire sections of the ground could become unstable. In the most extreme scenario, if magma were to find a pathway to the surface through one of these cracks, it could initiate a localized eruption, something that, while smaller than a full-scale supervolcanic event, could still cause immense destruction and prompt mass evacuations. Beyond the geological risks, the implications for human safety and environmental stewardship are vast. Yellowstone is not only a national treasure, but also a magnet for millions of visitors annually. The park's infrastructure, from its winding roads to its visitor centers, is ill-equipped to handle a rapid geologic event. Emergency teams are now re-evaluating their evacuation protocols and hazard mapping, anticipating various scenarios from localized hydrothermal explosions to more extensive ground collapses. The ripple effects of this red alert extend beyond the borders of Yellowstone itself. Local towns like West Yellowstone, Gardner, and Cody, which rely heavily on tourism and park-related commerce, now face uncertainty. The potential for longer-term park closures or restricted access could severely impact local economies. Moreover, broader state and federal agencies are on alert, recognizing that a significant geological event in Yellowstone would have cascading effects. Air travel disruptions, shifts in climate from ash dispersion, and strain on emergency response systems across the country. The public reaction has been a mixture of concern, fascination, and speculation. Social media is ablaze with satellite images, crack photos, and theories ranging from grounded geological hypotheses to wildly speculative doomsday scenarios. While some voices attempt to calm the situation, others point out that humanity has never truly witnessed the scale of what Yellowstone could unleash. The issuance of a red alert, while procedural in many respects, is not taken lightly, especially not in a place where past eruptions have been cataclysmic. Scientists, however, caution against jumping to conclusions. The park has experienced episodes of increased geothermal and seismic activity before, sometimes accompanied by surface deformation, hot spring disturbances, and minor quakes. Many of these have subsided without event. Yet, the difference now lies in the combination of signs: the persistent uplift, the expanding fissures, the ground cracking in non-traditional areas. It's not one anomaly, but a convergence of factors that has made this event stand out. Instrument networks across the park are now operating at full capacity. Tilt meters, GPS arrays, and thermal cameras are streaming data continuously, building a real-time picture of the subterranean forces at play. Helicopter surveys continue to fly over the park, documenting new changes from the air, while field teams hike to remote zones to place sensors and collect gas samples from venting cracks. The data collection is feverish and comprehensive, reflecting the seriousness with which scientists are treating this event. As the cracks continue to shift and expand, one central question looms over the effort. Is this the beginning of something larger, or simply another pulse in Yellowstone's complex geologic heartbeat? No one yet has a definitive answer. The park's history is one of massive forces at work over immense spans of time. Human observation, relatively recent and limited, is just beginning to scratch the surface of understanding this colossal volcanic system. Every crack that opens is a window into those deeper mysteries, a reminder that beneath the peaceful forests and bubbling springs lies one of the most potent engines of geologic change on the planet. What complicates matters further is the unpredictable nature of hydrothermal systems. These systems, which involve superheated water circulating deep underground, are particularly susceptible to pressure changes. A newly formed crack can redirect fluid flow, create pockets of trapped steam, or shift the chemistry of a geyser's eruption pattern. Over the past few weeks, there have already been anecdotal reports of geysers behaving erratically, either erupting with more force or ceasing activity altogether. While not yet confirmed as related to the cracks, these signs are being examined carefully. Moreover, the timing of the alert, issued during the park's busy summer season, adds a layer of complexity. Yellowstone draws millions of visitors annually, And the presence of unstable ground poses not just a safety hazard, but a logistical challenge. Trails near affected zones have been closed off, and backcountry permits revoked in select areas. Rangers have been trained to spot potential signs of new fractures and are equipped with satellite phones to communicate any developments instantly. The safety of parkgoers now depends on the precision and speed of information sharing among geological teams and the National Park Service. From a geological perspective, this situation also presents an unprecedented opportunity. The formation of cracks in real time allows scientists to observe a potential precursor process that has historically only been inferred through ancient rock layers and eruption remnants. Every sensor reading, every seismic signal, and every inch of widening crack brings new data points that could, one day, refine predictive models, not just for Yellowstone, but for other calderas worldwide. Still, the mood among many scientists is one of cautious vigilance. There is no guarantee that these cracks will lead to an eruption. They could stall, seal over, or be mitigated by other subsurface processes that relieve the pressure naturally. But there's also no guarantee that they won't evolve into something more dangerous. Yellowstone is a place where Earth's inner dynamics come closest to the surface, where steam, rock, and time intersect to create something both beautiful and potentially terrifying. The current red alert is not a declaration of doom, but it is a rare acknowledgement that something critical is unfolding, and it must be watched with the utmost care. Until further data reveals the true scale and meaning of these newly discovered cracks, Yellowstone remains under intense scrutiny. Every shift in temperature, every tremor, and every centimeter of ground movement is now part of a narrative still being written deep within the Earth. As eyes across the world turn toward this ancient caldera, the question remains, what, if anything, is about to awaken beneath the surface? The ongoing situation in Yellowstone has brought unprecedented attention to the complexity and volatile nature of volcanic landscapes. With the issuance of a red alert following the sudden emergence of cracks, focus has now shifted to the deeper scientific, environmental, and societal implications of this development. This event is not simply a matter of monitoring fractures in the Earth. It is a moment that could redefine how geological threats are perceived, prepared for, and integrated into national response strategies. The detection of fissures across Yellowstone's surface has triggered a multifaceted scientific response, drawing expertise from volcanologists, structural geologists, hydrologists, atmospheric scientists, and remote sensing analysts. Each of these disciplines plays a unique role in deciphering the signals being emitted from deep within the Earth. One of the most urgent efforts has centered around mapping the spatial distribution of the cracks with high precision. Using LiDAR scans, drones equipped with multispectral imaging, and satellite-based interferometry, researchers are creating detailed topographic maps that reveal not just the locations of the cracks, but the subtle vertical and lateral shifts in the terrain. These data points are being fed into evolving simulation models that attempt to predict how the ground may respond in the coming days, weeks, or even months. Parallel to the ground-focused investigation is a concentrated study of Yellowstone's subterranean environment. Geophysical tools such as magnetotelluric imaging and gravity mapping are being deployed to observe changes in magma movement and the behavior of hydrothermal fluids. Subtle shifts in electromagnetic fields can reveal the migration of molten material, and variations in gravity can indicate changes in subsurface mass distribution. Together, these metrics help scientists construct a dynamic 3D model of Yellowstone's inner structure, allowing them to see in near real time how energy is building or dissipating beneath the surface. Environmental biologists are also playing a vital role in interpreting the implications of these geological disturbances. Yellowstone is a living ecosystem teeming with wildlife and rare plant life that evolved alongside, and often because of, its geothermal activity. Cracks that alter the flow of steam, water, or heat can disrupt delicate microbial colonies that exist only in the hot springs and fumaroles. Even slight temperature shifts can collapse one habitat while opening another, potentially leading to cascading changes in species distribution. Observers have already noted unusual animal behavior. Bison herds moving to higher elevations uncharacteristically early, birds abandoning nesting sites near geothermal zones, and insect swarms appearing in locations where they are rarely seen. Such behaviors are not just curiosities. In many cases, animals have shown the ability to detect shifts in the Earth's magnetic field, pressure, and vibration long before human instruments can register them. While anecdotal, these observations are being cataloged and cross-referenced with seismic data to seek patterns that might strengthen predictive capability. If animals are indeed responding to stress deep underground, it adds another layer of concern to the already tense monitoring efforts. Infrastructure vulnerability is now under a microscope. Much of Yellowstone's roads and buildings are built atop thermally active ground. With cracks appearing in previously stable regions, attention has turned to evaluating the park's bridges, culverts, and communication systems. Engineers are assessing whether expanding fissures could intersect critical routes, compromising evacuation plans, or hindering emergency services. Park administrators are working with federal agencies to develop rapid deployment strategies, pre-positioning vehicles, supplies, and mobile command units at various points around the park to reduce response time in case of sudden deterioration. One of the more unexpected elements of the crisis is its technological dimension. Yellowstone has long been monitored using seismic stations and thermal cameras, but the current red alert has driven a surge in technological innovation. Researchers have launched experimental sensor networks designed to listen to the sounds of the Earth. Ultra-sensitive microphones buried in boreholes that can detect low-frequency acoustic signals emitted by moving magma or escaping gases. These infrasonic signals, often imperceptible to the human ear, can precede visible surface changes and provide valuable early warnings. Complementing this auditory surveillance is a growing use of artificial intelligence in interpreting the data flood coming from Yellowstone. Machine learning models are being trained on decades of seismic and geothermal data, enabling them to detect patterns and anomalies that may escape human analysis. These systems are not yet decision makers, but they function as powerful assistants, flagging subtle correlations between ground tilt, gas emissions, and temperature fluctuations that might suggest an impending shift in activity. On the chemical front, gas sampling is revealing changes in the emissions from new and existing geothermal vents. Elevated levels of carbon dioxide and sulfur dioxide can suggest fresh magma intrusion or the fracturing of gas-sealed rock layers. The recent emergence of cracks has made it possible to access areas previously unreachable. Teams in protective gear are collecting real-time gas samples, comparing them to baseline readings taken over the past decades. Even a slight change in gas ratios can offer insight into the type and depth of magma movement. Public communication is being handled with a delicacy seldom seen in national parks. On one hand, officials must convey the seriousness of the situation. On the other, they must avoid triggering unnecessary panic. The messaging strategy has shifted toward transparency, daily briefings, public dashboards of seismic activity, and educational materials distributed both at park entry points and online. Scientists are holding live stream Quanda sessions to explain the data and address public fears. The goal is to empower the public with information rather than let fear dominate the discourse. The media, both traditional and social, has created an atmosphere of heightened alertness. Amateur drone operators are uploading images of the cracks to online platforms, often with speculative captions. Satellite companies have released high-resolution images showing the visible damage, which are being dissected by internet communities and geology enthusiasts alike. While this public interest drives awareness, it also presents challenges, particularly when misinformation spreads faster than verified science. Park officials are now actively monitoring misinformation trends, working with social media platforms to flag dangerous or misleading content. Politically, the Yellowstone Red Alert has ignited a flurry of activity in Washington. Lawmakers are calling for increased funding for the United States Volcano Observatory Program and better coordination between agencies like FEMA, USGS, and the Department of the Interior. Committees are being briefed on worst-case scenarios, including contingency plans for large-scale evacuations, ash fallout across the Midwest, and disruptions to energy and transportation sectors. Though a catastrophic eruption remains an unlikely scenario, the government is treating the event as a real-time stress test of national readiness. Insurance and financial sectors are also beginning to respond. Analysts are recalculating risk models for properties across Wyoming, Montana, and Idaho, adjusting premiums and examining potential liabilities. Companies operating in Yellowstone-related tourism are reassessing their strategies, with some canceling upcoming trips, while others attempt to reassure clients with safety guarantees. Economists are quietly modeling the long-term consequences of an event that could potentially displace tens of thousands and depress property values across a large swath of the American West. Internationally, the event has sparked interest among global geological institutions. Yellowstone is not just a national icon, it is a global case study in supervolcanic behavior. Research institutions from Japan, Iceland, Italy, and Indonesia, countries with their own volcanic challenges, are offering support and sharing their expertise. The coordination is becoming something of a global collaboration, with shared data repositories and scientific symposia being organized to examine Yellowstone's unique situation in the broader context of planetary geodynamics. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on cracks in Yellowstone? We want to hear from you. Thank you for watching and see you next time.